Tell you about Velvet. I will have to sit for this talk, not just because I made it all the way from Singapore, but because that's a demo-based talk, and actually you can get all this, all the code I will be showing you on these links. But without further ado, let's check out the code. You can see the lin file, which oh no. Okay. Yeah, let me try to. All right. Yeah, somehow I cannot mirror the screen. But
Control F1.
Control F1.
Or Command F1.
No, nothing happened. Okay, let me just. Let's try this way. It's gonna be fun.
You can take 2 seconds to duplicate the screen, otherwise it will be hard.
Yeah. I mean, honestly, I'm not even sure what the what file is that. Yep. Okay, I guess I will have to sit like this. All right, this is the lin file, which might be a bit surprising because we are on the Dafny workshop. So aren't we supposed to talk about Dafny or?
Increase the font.
Yes. Like this is fine. Okay.
Awesome.
So we are supposed to talk about Dafny, or like at least autoactive verifiers. And well, we implemented one in lin, and now I will try to convince you that that was a good idea. Well, you can see the very first example of the program verified in Velvet. This is the square root. It's an imperative-looking style code with some annotations. You can also run this program, of course. Well, the square root of 9 is 3, so it seems correct. It's also correct on other numbers. I checked last time. So yeah, and now we want to verify it in lin, right? So how do we kind of do this kind of Dafny-like verification in lin? For this, we have a special command, proof correct, and the tactic, which will generate us a bunch of verification conditions as pure lin goals, which are equivalent to the soundness statement of this program. You can see there are a few of them, and well, now you can just go on and prove them using lin tactics, or maybe with some automation. So one way to do automated proofs is basically just that's a parameter in Velvet. You can say, well, try to prove them with CVC5. And you can see that it managed to prove everything with CVC5 using the lin auto backend, which connects lin goals to SMT. Yep, and well, so far nothing really surprising, but remember that in the title of the talk, we had this cryptic phrase, multi-modal. What does it mean? It means multiple things, but for example, Velvet has multiple semantics modes for the verification. For example, this loop. We have a while loop. You might be wondering if we prove the total correctness or partial correctness. Do we want to ensure that this loop terminates? And that's exactly what is the parameter in while. So you can set it up yourself. And one way to, so the way to set it up is basically using lin options. The option that is responsible for the termination is this one, and you can make it either partial total. I will show you the total example a bit later. Another thing that you can control is the semantics of a non-deterministic choice. Well, let me show you the program that uses this non-deterministic choice first. So this is a very simple program which converts the Boolean predicate on a finite type to an array. Well, so you see, one thing is that the predicate is mutable because we will be chopping elements from it one by one and basically pushing them into the array. So the specification is here. We have to, because the variable is mutable, we have to refer to its initial value, and the convention in Velvet is just you put the old suffix. Well, now in the loop, you basically pick the element non-deterministically. This is this set phase from Dafny, which is called Hilbert choice operator, basically non-deterministic choice. And now you can run this program. When you run it, this non-deterministic choice means basically random sampling. But when you verify it, because we just set it to demonic, that means that the semantics of this non-deterministic choice would be just for all quantification. So we will have to prove our specification, basically accounting for all possible choices that could have been made. Also, it also makes sense in some other applications to use the existential quantifier semantics for non-deterministic choice. This is very useful for symbolic bug finding, but I won't be showing this example here. You can find it in the paper. Yep. So now let's go and see a little bit more complicated example, which is the insertion sort. This is the code in Dafny, and this is how it looks in Velvet. More or less the same code and more or less the same annotations. But now let's get back to multimodal part. In Velvet, we can not only just symbolically verify the code, but we also can try to find shallow bugs using property-based testing. Yep, and let me show the example. So let's mess up our specification a bit and make it too strong. Yeah, a bit too strong. So now there are a bunch of comments, and the property-based tester, this is a simple code for it, will immediately give us the input for which the post condition is violated. You see that this input contains at least 2 repetitions of -8. So yeah, that's the way how you can use property-based testing. And also, of course, our verifier will say, oh, actually, I cannot prove this assertion. And the coolest part is that you can go on here and see the whole context, which is basically with all the facts that are true when you want to prove this assertion. And you can debug it here right now. OK, let's now do something else. Oh, no. OK, whatever. This should work too. So we will make our specification sound again. And here. And now we'll mess up with the code a little bit. So let's remove this line, which is responsible for the progress. Without this line, our program will just loop forever. And the question to the audience, do you think it will still verify? Yeah, it is partial. And yes, that's why it will verify. So it does verify here. No goals. Yeah, that's because it's partial. So as I promised, this is a parameter, so we can change it and make it total by uncommenting this line. Yep, and now as soon as we uncomment this line, you can see that Velvet now tells us, oh, actually, you need decreasing annotations if you want to verify it in the total correctness semantics. So let's just add those decreasing annotations right away. Luckily, I have them here. And now it will think for a second, or maybe 2 seconds, and verify it again, because I need to comment out the partial one. All right. So now it will think for a second and finally give us what it was supposed to give in the very beginning. Basically, it will say, oh, I cannot verify this decreasing annotation. And now you can basically look at the context and try to debug it. But luckily, we know what is causing the issue, this line. So we can comment it in back. And then the program will be verified. This is actually not the only way how one can play with different semantics in Velvet. One more way is the benefit of building autoactive prover on top of the foundational proof assistant, because you can now take the proofs and manipulate them as first order citizen and combine them to have something stronger. For example, for the same insertion sort, you can first prove it under the you can first prove determination. So here you can see you have the total semantics, right? And you only prove the post condition, which is just true. So you only have annotations related to the verification, to the termination. So that's one proof. And then you can also separately prove the partial correctness with the desired specification. So something that we have seen just now. And using these two proofs, you can rewrite your programs without any annotations with the spec that you're interested in and prove it in the total correctness without even calling any automation. You just basically combine the two proofs that you had before and use this lemma which says that, well, you can build the total correctness out of termination and partial correctness. So that was one way how we benefit from building attractive provers on top of Lean in this case. And another way which you might be more interested in is using interactive mode when in Lean tactics when automation fails. So the example here is the function which we implement ourselves. This is the function which computes if some number is prime or not. So it is fairly simple implementation. And then if you will try to run it, so here I disable automation for a second, so you can see that it generates 15 goals. And now if I remove this line to bring automation back, it will solve everything except one goal. So now we can just go ahead and try to prove it manually. But hey, aren't we in 2K26? I heard that there are so many, like bazillions of different LLMs which are incredibly good in proving pure Lean goals. Can we just try one of them and see what will happen? So we have a simple script which basically hoists the goals that we have in the proof correct statement as the theorems. And then you can put sorry and use the LLM of choice, Claude Code, Aristotle, what have you. And here, it actually produced a proof. You see the proof is quite involved. One interesting fact is that it uses Aesop cut, which is the Aesop tactic with some category theory tuning. Apparently, this is useful, I guess, in this proof. But the point is that this is an involved proof. So let's see what it actually tries to prove. It proves that basically your the number is prime, is not prime, is prime if and only if it has no dividers between 2 and the square root of this number. So this is not exactly a trivial fact. But you can still automate it fully with Velvet and AI, which means that Velvet kind of bridges the gap between all this success in AI for math and what we care about as popular community, software foundation, software verification.
Question. So how did the AI work though? I mean, is it that file?
Oh yeah, I don't show how AI works, but basically you put sorry here, and then you say, oh, either you say, okay, can you please fill this sorry, or you use some scripts in case if you, for example, do Aristotle. So somehow you.
So you let Claude edit that file?
Yes, yeah, exactly. But that's not the most impressive examples. We have another program which actually is not written by us. This is from some other project. This is a memory allocator. So this is a function which does some graphs labeling. It doesn't really matter. It's just not a entirely trivial function. Let's see what happens if we try to verify it with LoomSolve. Well, okay, yeah. It leaves us 7 goals to prove manually. And well, we run our script again, we hoist them, and ask AI to prove it. Well, it managed to. It actually takes quite a bit of time. Let me explain why. There is one beast goal. It has a. I cannot, I guess, now describe what does it mean exactly, but it's called goal 6. Yep. And yep. So the proof is quite involved, but that's not. But it actually gets cooler. To prove this goal, AI had to come up with the whole small small theory of facts about acyclic path, and it goes on and on and on. All these things are AI generated. Yeah, this helps us remind us about acyclic path. That means that now using kind of Velvet plus AI, you can automate the tasks which require developing theories. And this is, I think, quite cool. Yeah, that was it with the demo. I will see if I can. Oh no. Oh, yes. Yeah, okay, it works. Just a couple of seconds. If you're interested, some couple of forward pointers. If you're interested in the foundations of Velvet itself as a tool, you can visit my talk on Friday. The tool is called Loom. This is foundations for all these kind of provers. Then, if you're interested in other things that we built on top of Loom, so Velvet-like verifiers, you can stay for a bit. George will give a talk on Veil. That's after lunch. That's the verifier for distributed protocols, and also George and Qiyuan, they will give tutorials on this tool. I really suggest you visiting it because this is also mind-blowing. Yep, that's it. That was Velvet. Thank you very much for your attention.
Okay. First of all, that's really, really cool. And second, my question is, does your AI also generate the invariants and ensures and for alls? I mean, ensures and requires, sorry, I guess you don't want to generate them because that's what you want to prove. But the invariants, do you generate them at all, or?
Yes, we have some experiments that we try, and it actually, I guess stay tuned, we will have some work about it. But yes, we tried, and it actually works. But one thing that really helps when it has some suggestions for like invariants, right? It really helps that we can execute our code and basically property-based test invariants as well. So this will kind of help it to have the feedback loop, and that's quite important. Yeah.
Thank you for the talk. So I was curious about how do you handle recursive functions at all?
Oh yeah, that's a great question. We right now redesigning a bit the framework to have the better support for basically arbitrary recursive functions with the kind of also total partial correctness proof. But at this point, with the recursion, we only handle the well-founded recursion. So basically, the recursion where lean can make sure that the program terminates. And then you will have to do basically this standard lean extrinsic proofs that function terminates. Yeah.
It's something like the 91 function, right, where you have the proof of the. There you go, the classic.
That's not the first time we got this question, and that's exactly why we are redesigning it to support arbitrary recursion. But yeah, it's possible. It's really technical reasons why it doesn't work exactly there, but it should, yeah.
Yes. Okay, cool. Yeah, I'm very bought into this stuff, so this is very cool. The title of the talk said Effectful programs. So I see mutability here, but I'm just wondering if you've considered other program effects.
Yeah, that's a great question. So the other program effects which we consider in Velvet are non-determinism and non-termination. This is for Velvet. We're thinking of adding exceptions, but so basically we have this library of kind of effects and the ways to deal with them, which is called Loom. So please visit my talk on Friday where I will tell much more about that. But another thing is in Veil, that's another framework for these Veil protocols. We support much more effects, including also exceptions, state, only read-only state, and stuff like that. So yeah, different kind of effects are supported. We have this special library for that.
Lunch. Let's thank the speaker again.